Okay, so to wrap up this unit, we've talked about three major transformations, of which there are two of each, for a total of 6 transformations. We started with shifts. You can shift graphs horizontally and vertically. We then went to stretches, which you can also do horizontally and vertically. And then we went to flips or reflections, which you can do horizontally or vertically. And then we combined all of them together. And that was, like I said, the majority of this unit. There is another type of relation that we're going to look at sort of separately. And it's something called the inverse of a relation. An inverse of a relation is actually pretty straightforward. All you do is you switch the x and y values. That's all inverse means. Technically, an inverse of a graph, like if you have a graph and you want to sketch its inverse, you would reflect it over the line y equals x. And the line y equals x, well, that's a line that you learned like way back, probably in middle school, if not the latest, grade 9. Y equals x is a straight line that runs diagonally through the origin. So an inverse is like a flip, except you're not flipping it over the y-axis like a horizontal. You're not flipping it over the x-axis like a vertical. You sort of cock your head 45 degrees and you're flipping it over this line. And what's the same? That's the same as taking every x and y value of a point on the graph and switching it. So on the original graph, if we've got the points x, y, if we're going to draw the inverse to find the points on the inverse to sketch its graph, we just flip the x and y coordinates of the points. So we can find the inverses of relations and functions in any form. Remember, relations and functions, they could be given to you as a set of ordered pairs. They could be given to you as an equation. They could be given to you as a graph. So you may be asked, you may be given one of those forms of a relation or function and asked to find its inverse. Don't overthink this, okay? Let's say I've given you a relation, and I believe it's also a function because the domain values never repeat, okay? And I ask you to find the inverse. So that would be the same as plot these 4 points on a graph and then flip it over that line y equals x. What are the new points? Well, I don't have to do all that work, okay? How do I find the inverse? I just take every point and reverse it. And by the way, when we're talking about, this is not a negative exponent. It does not mean a negative exponent. It's just the notation that we use for inverse, a little -1 up and to the right. So how do you find the inverse of these 4 points? Reverse them all. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. 3, 6 becomes 6, 3. And 4, 8 becomes 8, 4. So taking an inverse of a set of coordinates is really easy. Don't overthink it. Just flip all the coordinates, switch all the coordinates, the x and y values. Finding the inverse of an equation is a little bit more, it takes a little bit more work, but it's still the same idea. Remember, and here's the steps. So let's say we have this equation. What would that look like if you graphed it, by the way? It would just be a line, wouldn't it? Yeah, that's all. So it'd be like graphing a line and then flipping it over that line, y equals x. But to do it algebraically, remember, this is just notation that means function. I can also write a y here. So f of x equals 2x plus 1 means the exact same thing as y equals 2x plus 1. Now I'm actually going to find the inverse of the equation. How do you find the inverse? Reverse the x and y. So switch them. So this is the actual inverse of this, because I just switched the x and y's. But it's not in a form that's acceptable. Normally, when we write an equation that we're going to work with of a function or a relation, we want y by itself, like we have here. The original function y was by itself, and the rest of it with x was on the right-hand side. After I inverted it, I need to solve for y. So how do I solve for y? Well, I got to bring the 1 over to the other side by subtracting both sides by 1. And I got to get rid of the times 2 to get y by itself by dividing both sides by 2. I'm going to put it over here. These mean the same thing. It's just this, it's solved, the equation is solved for x, this, it's solved for y. But they're the same thing. Okay? Now, this is very important. If you're asked to write the inverse, you've got to use inverse notation. So you've got to use this little -1 thing. If it is a function. Well, if you graph this, it would also be a line. And any line except for a vertical is a function. So all we would do is take this and replace the y with f inverse of x equals x minus 1. Those are the steps to find the inverse of an equation, of a relation or function. Just because the original is a function doesn't mean the inverse will be. In this case, they are, but not in all cases. I'm going to show you an example. Okay. And so inverse, think of it as like undoing, reversing things. So if you think in the first one, well, we took every x value, we times it by 2 and then added 1 to get the y. Well, the inverse would be start with the y, take away 1, and then divide 2. That's the very definition of inverse. Okay? So if we're in the original, if we're getting every y by going times 2, add 1, then it makes sense that we would take, in the inverse, we would take the inverse value, the x value, input value. I knew it. I knew it. Subtract 1, then divide 2. So we've seen how to deal with an inverse of a set of points, set of coordinates. We've seen how to deal with the inverse of an equation, okay, using algebra. Let's look at an example graphically and algebraically, both. So we are asked to find the inverse of g of x equals x squared minus 1 algebraically. So let's just ignore this for a second. So to find this algebraically, first I replace this with y. Now to find the inverse, switch the x and y. And now you got to get y by itself. Add 1 to both sides. Ooh, how do I get rid of the squared? Yeah, but remember when you square root, don't you have to take the positive and negative? So we would have to take the positive and negative square roots of the left-hand side. Now, notice I haven't put in the inverse notation yet. Here's x squared minus 1 on the graph. It's taking x squared, which starts at the vertex at 0, 0, and moving it 1 down. Is the red one, the red parabola, x squared minus 1, is that a function? Remember vertical line test? Can you draw a vertical line through more than one point on the red one? No. So this is a function, which means I can use this function notation. Okay. When we found the inverse, we got this. This here, sideways parabola, is actually the graph of the blue one. And we're actually going to study square root graphs in the next unit. Is the sideways parabola a function? No, it's not. So I can't use function notation. I can't use g to the negative 1. I have to leave it like this because it's not a function. Okay? So why can't we call the inverse? Why can't we use this notation? Because the inverse is not a function. And why? Because we can draw a vertical line through more than one point. So if we take a function and we find its inverse may not necessarily be a function. You've seen an example where its inverse is a function above, and you've seen where its inverse is not a function, like in example 3. An interesting question to answer, at least interesting to me. Look at the original one, the red one. Is there any way, like, how much of the graph would you take out so that its inverse would be a function? So you got to think, see if you can do it visually. So here, I'm going to resketch it. And the red one is down here, so it goes like this. So I know that if I take this entire graph, the entire parabola, and if I find its inverse, it's not a function. What could I take out of this graph? Like slice it away. Half of it? Like half of it above and below? Half of it sideways. If, right now, this is not a function, but if I remove this and just kept the right side of the parabola, its inverse would be a function. Or I could cut out this side. There's more than one answer. Or I could cut out a whole bunch of stuff and just leave a little sliver left. There's infinite answers, but these are sort of the two obvious ones. So if we have a parabola, we know its inverse is not a function. To make any parabola's inverse a function, we need to cut half the parabola away. This is how we do it graphically. How do we show it using notation? Well, here, I'm restricting the domain. I've taken away half the parabola. The domain of any parabola, left to right, is everything, right? Negative infinity to positive infinity. But what's the domain of this? It's only from 0 to infinity. So that's how you would restrict the domain. So to answer this question, how would you restrict the domain? You'd change it to this, which is this. So this is notation for doing this graphically. What would the notation look like if you did it like this? What's left? Negative infinity to 0. So both answers are correct. Either one's correct. This is essentially inverse. So we just want to finish the rest of it with some different examples that you can see. Yeah.
For the first one where we found y equals the square root of x plus 1,
Yep.
would we have to say from only that information if it's a function or not? Or
you know, I would, we haven't studied these yet, so I wouldn't give it to you in this form. I would, if I was to give you a question, I would give you a graph. Like, let's say, actually, this is a good question. You don't have to write this down. Let's say I gave you this graph, which is an absolute value graph, V-shaped. What do you think? Is that a function? Yes. What do you think about its inverse? Well, let's make up some points. Let's call this 1, 2, 3, and then let's go like this. So we've got this one, we've got this one. Let's find the inverse of all these points. So the inverse of 0, 3 is 3, 0. So this one becomes here. The inverse of 1, 4 becomes 4, 1. So it becomes there. The inverse of 1, negative 1, 4 becomes 4, negative 1. That's its inverse. Is it a function? No. Okay. So I'm just going to throw different types of questions at you. I'm giving you two functions. And I want you to tell me whether they're inverses of each other. Why are you nodding? Not the exact same.
no, they're almost the same as negative.
Almost only counts in horseshoes and hand grenades. Sorry, I just wanted to use that line today. I just like that line. Okay, but you got to give me, yeah, that's not really an explanation to say that it's like the last example. But if you can explain to me why it's like the last example, then that's good. Zoe?
The first one is where the opposite minus 1 would be
So,
Like,
so if you went backwards from this one, so 2x, you take x times 2 plus 1 going backwards is plus 1 divided 2.
the 2 times is specified to the x only.
Say that again?
The 2 times x is only specified to the x, yeah.
Yes.
So the other one should be divided.
So you're saying for that reason it's not. They're not. Okay. No, that's good. That's good thinking. Ellie?
If you were to solve, like do the inverse of all the functions and f of x, end up with x plus 1 or the last bit on minus 1.
If you were to
If you were to do, like if you were to
find the inverse of this?
yeah, so if you were to solve 2x subtract 1 algebraically,
Yeah.
it would end up being like g of, what is it? G of x, except for the fact that it's plus 1 instead of negative 1.
Yes, but we also have to account for the 2 in there as well.
But then, but you're dividing it because it's algebraic.
So you're saying because you have a times 2 and a divide 2 in here, and a minus 1 and a plus 1 in here, they have to be inverses.
Yeah.
Okay. Where Zoe is saying, well, the times 2 only applies to the x, so the divide 2 should only apply to the x. Both very good arguments. Okay. One way you can do it, pick one of them and find its inverse. See if it equals the other one. So let's take this one. I guess I'm working in blue now. Let's find the inverse of it. See if it actually works out to this. So change the f of x to y, switch the x and y's. Oops. And then solve for y. Add 1 to both sides. Divide both sides by 2. Bless you. So when you do the inverse, you get this expression, which is g of x, which equals g of x, which means they are inverses of each other. But like I said, both arguments were very good. Because if you think about it, when I talked about the previous example, to find y here, I times 2 and then subtract 1. Well, going backwards, or the inverse, I add 1, then divide 2, which is exactly what this one is doing. Okay? So you want a final sentence here, therefore they are inverses. If I found the inverse of the first one and I didn't get this, then obviously you would say they're not inverses of each other. Example 5. This is one of those restricting domain questions. What's this shape if I graph it? It's a parabola because it's got a squared. It's got an x squared, okay? And we could actually graph this. Where's the vertex of x squared, the most basic one? Where's the vertex? 0, 0. But this one tells me to do what? Tells me to go to the right one. And that's 1. How would I restrict it? Cut away half of it. You decide which half you want to cut away. So if I decide to cut, like right now, if I find the inverse of any parabola, it's never a function. Okay? Same with the V shape that we did. But so I have to restrict the domain. So I'm going to cut off the left side. What remains? What domain remains? This time it's 1 to infinity. So that would be your answer. That's how you would restrict it. If you had negative infinity to 1, because you decided to cut off the right side of the graph, you are just as correct. Okay? We've done a little bit with graphing inverses. Let's look at a couple of examples. So for each of these examples, you're given the graph of the original, okay? And you're asked to sketch the graph of the inverse and name any invariant points. State the domain of the that's not quite right. State the domain and range of the relation. State the domain and range of the relation and its inverse relation is what I want to say. Fix that. Because I can't say function because I don't know if it's a function when I find the inverse. Okay. And then we want to determine whether the relation and its inverse are actual functions. So for the first one, here's the original. Two rays connected. So to graph the inverse, okay, I need points on the original. And then when I find the inverse, I'm going to take all those points on the original and switch the x and y's. So I want to make sure I account for all sections of the graph. So I'm going to do this one, and this one, even though I've got space for more. That should be enough to graph the inverse. If it broke off like this, then I'd want to pick a point on that portion too. But you want to make sure you cover all sections. Otherwise, you might miss the graph a little bit. So this is the point -2, 0. This is the point 1, 3. And this is 4, 3. Now we want to graph its inverse. So we take all these points and we reverse them. 0, -2, 3, 1, 3, 4. Like I said before, connect as you go. Don't just plot all the points, because I've seen it often that students will just plot these three, 0, 2, 3, 1, and 3, 4, and then they'll be like, oh, but how does it go? Does it go like that? And then they'll end up getting the incorrect graph. So what you want to do is graph. What I mean by graph as you go, do -2, 0, sorry, 0, -2, do 3, 1, and connect them. Do 3, 4, and connect them, and you should be able to see where the arrows go. They're going to go like this. And how can you tell if you've graphed an inverse correctly? Remember, I said it's reflected over the line, y = x. So what you could do is tilt your head 45 degrees. See, okay, if I tilt my head 45 degrees, and if I flip the red one over that blue line, do I get the purple one? And you will. Yeah? Thank you. I knew that looked a little off. Good catch. Ah. Cheat there. There. Yeah, that's much better. Before we move on to domain and range, any invariant points that you see that didn't change when I flipped and found the inverse? It stayed where it was? Yeah, good, good. We didn't have it on here, but where would you find those points, invariant points? Any points that are on the blue line would be invariant. Because if it's on the line and you flip it over the line, it's still on the line. So this point here, 3, 3, would actually be an invariant point. That cleared it up. Oh my God. There. Okay. What's the domain of the original one? Negative infinity to positive infinity. Remember, there is another way you can write this domain and range using set notation. I'm just going to stick with interval. What's the range? Careful with this one. Negative infinity to 3. Look at the purple one. That's the inverse one. What's the domain of that one? Furthest left, negative infinity. Furthest right, where? Furthest right is at 3. What's the range of the purple one? Lowest to highest? Well, it goes down forever and up forever, so negative infinity to positive infinity. No. Do you notice anything? Yeah. The domain and ranges are inverses of each other. So the domain of an original is the same as the range of its inverse. Actually, I'm going to write that. The domain of a relation is the same as the range of its inverse. And you could also say the range of a relation is the same as the domain of its inverse. So kind of like vice versa. The range of a relation is the same as the domain of its inverse. Final question we had to answer was look at the original graph and the inverse graph. Is the original graph a function? Yes. Yes, it is. Is the inverse one? No, it is not, because you can draw a vertical line through a lot more than one point. So to answer the final question, the original relation is a function but its inverse is not. I think we're going to stop there.